going to be on October 27. We're going to cover chapter 5 and 6. All right. So this will be under module 3, chapter 5 and 6. Can you see my slides on chapter 5? Chapter 5, gases and liquid and solids. Can you see it?
Yes.
Okay. Let me start from the beginning. Test going to be on October 27 on chapter 5 and 6. So we had to do quiz 5, quiz 6, and then take the test on module 3. So the structure is same as what we had for module 1 and module 2, for chapter 1 and 2 and 3 and 4. So let's start on this now. Okay. Chapter 5 is on gases, liquids, and solids. We briefly talk about states of matter. These are the 3 states of matter that we find, the 3 forms of matter. So I'm having a difficult time. Okay, let me see. Okay, it doesn't matter. I may show up there. Chapter 5 is on gases, liquids, and solids. These are the 3 basic states that matter can exist. So we're going to focus on gases more here. First, we're going to talk about gases, then liquids, and little bit about solids. We already introduced you to 3 states of matter: gases, liquids, and solids. These are the 3 forms of matter. Gases are different from liquid and solids. Gas is only 3 state of matter which shows up a pressure. Pressure is only coming from gases. There's no pressure exerted on us by solids and liquids. So we mainly going to talk about gaseous behavior after we talk about how we measure pressure. There are 4 laws that describe this gas behavior. 4 laws. They are Boyle's law, Charles' law, Gay-Lussac law, and Avogadro's law. The 3 laws we didn't mention here: Boyle's law, Charles' law, Gay-Lussac law. 4th law is the Avogadro's law. And 5th law is the Dalton law. This is about pressure. Dalton's law of partial pressure. We're going to talk about this when you deal with mixture of gases. After we go on over gas laws, which are 5 of them, 6 of them, including last one is Dalton's law of partial pressure. We need to explain our gas laws. Like in atomic theory, we have chemical laws. Laws conservation of mass, law of constant proportion, law of multiple proportion. These are similar to Avogadro, Boyle's law, Charles' law, Gay-Lussac's law, Dalton's law, etc., ideal gas law. We come up with the theory called kinetic molecular theory of gases. This is for gas. Kinetic molecular theory in modified form is also used for liquids and solids. We're going to look into that when the time comes. Now, basic difference between gases, liquid, and solids. What state of matter certain compound adapt is dependent on intermolecular attractive forces between molecules. So these states of matter, these three states of matter, gases, liquid, and solids, applies only to covalent compounds. Ionic compounds are solid, therefore they are always solid. But covalent compounds have lower intermolecular forces. Intermolecular forces are not that strong. Like ionic forces, ionic bond is very strong. Therefore, covalent compounds exist as gases, liquids, and solids, depending on the intermolecular attractive forces. We're going to look into this. So after we finish gases, we're going to look at the liquids. I'm going to come back to this after we've gone over and revised it again in next class period. So we're going to start with three states of matter. We already gone over this. We are familiar with this. Let me stop share. This picture is solid state of water, ice. Water in the solid state is arranged in fixed positions, regular arrangement. Solid show regular arrangement. This is the solid state. Liquid state, water, which is the water molecules roll over each other. They are flowing. Solid state doesn't flow. Gaseous state is a free state that can move around the space given to the gas. So when we describe solids, we have to know their properties. Solid has a definite volume. It doesn't have a definite shape. Liquid has a definite volume. Also, gas have no definite shape or volume. The shapes are, liquid has the shape of the container, solid has its own shape. It maintains shape regardless of its container. Liquids take up the shape of the container because it can flow. Gases fill into the volume of the container and fills up. Solid particles lie close to each other in a regular pattern. Liquid particles are held together but close, but they can move around. Gas particles are far apart and move around randomly. This is the molecular description of three states of matter. particle description. Now let's look at the gases. One of the important property of a gas is pressure. We call it, normally we give a symbol for P is the big P, pressure. How we measure pressure depend on the units we use. Each measurement in the scientific method has a unit. So pressure has unit. Pressure is the force exerted against the surface of the container, balloon, flask, or whatever it is, closed container, which take up the gas. Pressure is felt by the wall of the container. Most commonly measured pressure unit is millimeter mercury. This is also called torr. And I'm going to show you another unit is ATM pressure. Okay, 1 atmospheric pressure. We're going to see how much millimeter mercury or torr is 1 atmospheric pressure. 1 atmospheric pressure is 760 millimeter mercury or torr. This is same as torr. 760 torr, 1 atmospheric pressure. SI units, scientific units, use Pascal. So it is 100,000, 325 pascals. 1 atmospheric also this 760 torr converted to millimeter, converted to this, millimeter to inch conversion. That's 29.92 inches of mercury. So let's look at how we got 760 millimeters. There's another one called bar. It's roughly about 1 atmospheric pressure is equal to 1 bar. That means 5 bars are 5 atmospheric pressure. Atmospheric pressure is measured using a barometer. Barometer is a device which measures the pressure in the atmosphere. I'm going to show you this. There is also another device called manometer, which only measures the pressure of a certain container. This is not the atmospheric pressure. You can, from a gas well, you can measure how much pressure is exerted by the gas well. Let's look at the barometer. Barometer is the basic idea for measuring pressure. Barometer was created by Torricelli, Italian scientist. What he did was this. He took up an open end tube. Here it's open, one end is closed. He turned this around. I cannot draw. Fill it up with mercury. Then he turned around and pushed that into the container with mercury. When you get there, there's full of mercury here. But this always drops down, no matter how careful it is. There's a vacuum in here. There's nothing in there. This height of the mercury column for 1 atmospheric pressure is roughly equal to 760 millimeter mercury. That's how we know 1 atmospheric pressure is 160 to millimeter mercury. What this means is a pressure, atmospheric pressure is exerted on the mercury. It balances by this much of a mercury column. Therefore, all the weight in the atmosphere is balanced by 760 millimeter mercury column. So therefore, 1 atmospheric pressure is 760 millimeter mercury or TOR. That's how we come up with idea about 1 atmosphere and 1 barometer, from the barometer. 1 atmosphere is equal to 762. When you're trying to measure pressure of a container, right here, this is hooked up to a gas well. You collect a sample from the gas well. And the pressure is here, just like barometer. This is called manometer. It's small scale. The pressure of the vessel is 80 here. So gas wells also important for our economy. We measure how much pressure exerted by gas wells. It indicates how much natural gas in the well. So manometer is used to measure gas inlet pressures. Now we know what is pressure. Pressure is exerted by a gas on the wall of the container. Force per unit area expressed in TOR, millimeter mercury, 1 atmosphere, Pascal, bar. There are several units. Now we're going to look into other properties. We already talked about pressure. Gas also has a volume. Normally it's in liters. This is ATM. Normally we do it in ATM or TOR. Temperature is measured in Kelvin units. So there are 3 variables: pressure, volume, and temperature. There's a fourth variable, which is the amount of gas in moles. We're going to look into that in Avogadro's law. So what they did was, when they discovered the gases, they hold these 4 variables, 1, 2, 3, 4. Fourth one is this. Two, 3. No, that's not the 3. That's the third one. That's the fourth one. PVTM. To study effect of one on other things, you had to hold a T constant to an N constant to see the effect of pressure and volume. Let's look at how the pressure and volume changes on the gas. For a fixed mass, that means N is equal to constant. At constant temperature, N and T is constant, held constant. T is the Kelvin temperature. What is the effect of volume on pressure? Volume of a gas, right here. is inversely proportional to pressure. Pressure is inversely means 1 over P. This symbol is called proportionality symbol. When you have 1 over proportionality is inverse proportion. When you rearrange this one, you take the PV, proportionality is equal to 1. Therefore, it is equal to a constant. So PV is equal to constant according to Charles' law, Boyle's law. So to get rid of constant, this is mathematically done. You take 2 readings. P1 is initial, P1, V2 is initial volume, initial pressure, P1, final pressure, P2, final pressure, V2, 2 readings, 1 and 2. Then that gives the Charles' law equation, Boyle's law equation. If you look at the volume and temperature, which is the subject of this is V and P, while N and P held constant. This is N and T held constant. Charles' law says it's directly proportional. Just like the previous example, V is directly proportional to T. Therefore, V divided by T is a constant. You take 2 readings, just like in the Boyle's law, Charles' law equation become V1 divided by T1 is equal to V2 divided by T2. Boyle's law is P1 times V1 is equal to P2 times V2. These are used in calculation. I'm going to show you this. So there's another law called Gay-Lussac's law. Gay-Lussac's law is pressure versus temperature. N and V is held constant. It's a constant volume here. Fixed mass of gas is N1 is constant. Volume is constant here. Moles constant. So it's just like the Charles law. P1 divided by T1, T1 is equal to P2 divided. This is the third equation. It's called Gay-Lussac's law. In summary, there are 3 gas laws when you investigate. Effect of pressure over volume, volume over T, pressure over T. These are Kelvin temperature. T is Kelvin temperature. You get 3 equations. We described 3 equations. These are the earliest gas laws. Boyle's law, Charles' law, Gay-Lussac's law. We also come up with another one called combined gas law. We combine all these 3 equations into a one, where it says PV divided by T1 is constant. To remove the constant, you take 2 readings here, P1, V1, T1 divided by T1 is equal to P2, V2. This equation could be used in place of any of the 3 previous equations. All right, in addition to pressure and volume and temperature, all pressure, volume, and temperature, all are combined. This is called the combined gas law. Let's do a calculation. A gas takes up 3.0 liters of volume. That's the volume. That's the pressure, 2 atmospheric pressure. Calculate the volume. These are V1. P1. When the pressure is, the second pressure is 2. Volume. Question is, what is the V2? So you use the combined gas law, P1 V1 divided by T1 is equal to P2 V2. We solve for V2, P1 V1 divided by T1, then V2 divided by P2, T2 is the, all right. Then the constant pressure is, it's equal to P1 V1 divided by P2. So when you plug in this equation, T1 is equal to T2. So this is the same P1 V1 T1 T2 cancel. So P1 V1 is divided by P2 is, you plug in the values, P1 here, V1 here, P1 here, 3 liters, 2 atmospheric pressure divided by P2 is 10.51 here, P2. So final volume is 0.591 liters. That's how you calculate using combined gas law. Combined gas law is convenient. Now the second, third, fourth law is Avogadro's law. Avogadro's law deal with volume and of a gas, how it's dependent on number of moles of gas, amount of gas. So each volume of a gas at the same temperature pressure contains the same number of molecules. If you have a gas at same temperature and pressure, equal volume, two gases, that both gases have same number of molecules. This is the Avogadro's law. Avogadro is the one who came up with moles of material. 6.022 10 to the 23 is a mole of substance, molecules. It's called a mole, 1 mole of molecules. Avogadro's law is similar to Charles' law, V1 divided by N1 is equal to V2 N2, V2 divided by N2. When you are comparing, it doesn't matter which pressure and temperature you choose for the two gaseous samples. It always have two gaseous samples at any temperature and pressure, same temperature and pressure, has same number of gas particles, same number of moles. But for convenience in comparison, we can come up with what we call standard pressure and standard temperature. It's called STP. STP is defined for the Gay-Lussac's. Avogadro's law is standard temperature and pressure. Temperature is 0 degree Celsius or 273 K. We mainly use 273 K for gases and 1 atmospheric pressure. What is the standard temperature and pressure? 273 K and 1 atmospheric pressure. If you compare two gases, volumes of same moles of gas, they have same number, same volume also. All gases at standard temperature and pressure or any other combination of pressure and temperature contain the same number of molecules in a given volume. But how many molecules is that? 1 mole of molecules. We use moles in gas laws. What volume of the gas contains this many molecules? Is 22.4 liters of any gas at standard temperature pressure. 1 mole of any gas at standard temperature and pressure has a volume of 22.4. This is called molar volume at standard temperature and pressure. If someone asks you, what is the molar volume of a gas at standard temperature and pressure? Answer is 22.4. How do I get 22.4 liters of volume for 1 mole of gas at STP? We use another equation called ideal gas law. After Avogadro's law came about, they combine all 4 variables. PVTN, pressure, volume, temperature, and moles, into one equation with a constant, PV divided by RT. This constant is called ideal gas constant. We call it R right here, ideal gas constant. This is called ideal gas equation. So you can calculate knowing the moles, temperature, pressure, one of the unknowns. If you knew temperature, number of moles, volume, and ideal gas constant is known, you can calculate P or any other combinations of 5 variables. So you can use this equation when you have number of moles in mole. Previous example, we have fixed amount of gas, but in this case, moles of gas. Pressure of the gas is measured in ATM, volume is gas in ideal gas equation, ideal gas law equation, volume is measured in liters, N is measured in moles, temperature is measured in Kelvin. So you can do calculations using the ideal gas constant. Ideal gas constant is calculated based on the fact at standard temperature and pressure, 1 mole of a gas has 22.4 liters. So R is calculated using the 1 mole of gas at standard temperature, 273, 1 atmospheric pressure. So you plug in the equation, R is equal to, you rearrange the PV and RT. Normally you have PV is nRT. You solve for R, then you get R divided, R is equal to PV divided by NT. So you get these two in the bottom, leaving the. So P is 1 atmospheric pressure, V is 24 molar volume of a substance, gas, that's the standard temperature, standard pressure, 1 mole of gas. Ideal gas constant is 0.0821. If you use 762 in place of 1 atmosphere pressure, ideal gas constant is 0.821 multiplied by 760, which is 62.3. So sometimes if you use tau as a unit, ideal gas constant is 62 point liter to mol K. Ideal gas constant also has units. Now let's do a calculation. Let me get this out of the way. 1 mole of methane, that's a natural gas, has volume of 20 liters. The pressure is 1 atmosphere. What is the temperature of the Kelvin? So you have to solve for T. T is equal to, you rearrange this equation again. PV divided by NR. So you plug in this equation, whatever you have. This is the equation I also got right here. So units cancels out the temperature when you multiply 1 times 20 divided by 1 divided by 1, 0.0821, you get temperature of the gas, methane gas is Kelvin. If you need to, if the question was asked in Celsius, you have to subtract 273. Celsius plus 273 become Kelvin. Therefore, Kelvin subtracted 273 become Celsius. We done the temperature calculation before. Now we talked about Boyle's law, Charles' law, Gill-Sacks law, Avogadro's law, ideal gas law. Then the last one we have is Dalton's law of partial pressure about the gases. This applies to mixture of gases like atmosphere. Atmosphere is mixture of oxygen, nitrogen, carbon dioxide, and little bit of helium. Other gases, noble gases. Dalton law of partial pressure. This is the idea that sum is equal to partials. Mixture of gas, sum of the pressure is equal to partial pressure of each individual component of gas. This is the P total. P sub T is P total. This is the component one. It could be oxygen, nitrogen, and carbon dioxide, etc. Nitrogen. It all depends on the partial pressure. Partial pressure is defined as a pressure exerted by only that component of the gas. Pressure exerted by oxygen plus pressure exerted by nitrogen plus carbon dioxide is the atmospheric total pressure. Let's do a problem about this. Dalton law of partial pressure always applies to mixture of gases. Here's the question. Tank has nitrogen, oxygen, and little bit carbon dioxide. The total pressure of the tank (4.6) atmospheric pressure. I don't have to write all ATM. This should be equal to partials. Partial of nitrogen is 2. Partial of oxygen is 1. Then the partial of carbon dioxide, which is unknown. So this X could be calculated by rearranging. partial pressure of carbon dioxide is equal to 4.6 minus 2.0 minus 1.0. Which happened to be 0.16. So when you do this calculation, it shows up the partial pressure is 0.16 here. Answer is 1.6. I calculated it in previous screens. So that's how you calculate partial. When the total is given and other components are given, partial pressure. If you give all partials, asking for sum is easy. Okay. We done with 6 gas laws and some idea about how to use them in calculation. Now, like in atomic theory, after we came up with chemical laws, law of conservation of mass, law of constant proportion, law of multiple proportions, we had to come up with a theory to describe why gases behave that way, why they increase pressure, reduce the inversely pressure, volume is inversely proportional. Volume is directly proportional to the temperature, Charles' law. Then the Gay-Lussac's law, pressure is directly proportional to temperature. And Avogadro's law, volume is directly proportional to it. And ideal gas law, and Dalton's law of partial pressure, all has to be explained. To explain this behavior of gases, we have few assumptions, just like in atomic theory. They assume gases are made out of constantly moving particles through the space in random direction and with various speeds. They are random speeds. Some move faster, some move slower. They collide with each other, etc. Okay, there are no attractive forces between gas particles. Unlike in liquids and solids, there are attractive forces, intermolecular attractive forces. Gas particles are totally free. We assume that according to gas laws, to explain gas laws by kinetic molecular theory. Now, what is temperature? We had to define what is temperature. Temperature is the kinetic energy of the gas particles, directly proportional to. Temperature is directly proportional to the kinetic energy of the gas particles. Now, since gases maintain temperature, at certain temperature, it doesn't lose energy, gas particles, at certain temperature. These collisions between gas particles and the walls of the container must be elastic. Elastic means it doesn't lose any energy. So their kinetic energy remains constant. And also gas behavior. For example, 1 mole of gas has 22.4 liters of volume. Indicate that gas particles have almost no volume compared to the volume of a container. Therefore, we assume gas particles have no volumes. These are description of ideal gases. Molecules collide with wall of the container, and these collisions constitute the pressure of the gas. So pressure of the gas is defined by collision with the wall. Particles moving in random space while gases expand into volume given to the container. Temperature is defined. Pressure is defined. Okay, this is the assumptions in kinetic molecular theory for gases. Now, these are called ideal gas behavior. Gases at close to standard temperature and pressure, 1 atmosphere, 273 Kelvin, they behave like ideal gases. There are no attractions. Ideal gases have 6 assumptions I have shown previously. Particles of a gas and their interaction with one another describe the ideal gas in the previous assumption. Real gases are the one that we deal with. Real gases obeys. Real gases are close to ideal gases when their temperature is not very high. Temperature is high. Pressure is low. High temperature, low pressure. If you cool or compress, reduce the pressure. Compress is increase the pressure. Low pressure is decompression. If you cool or compress a gas, they become liquids. There are atoms or molecules do occupy some volume. Real gases have some volume, unlike the assumption in the kinetic molecular theory. But at the conditions we give, standard temperature and pressure, 1 atmospheric pressure, 273 Kelvin, 0 degrees Celsius, more real gas behave same way as predicted by CHEM. Real gases behave like ideal gases around the temperatures, pressures of STP. There are forces of attraction between their molecules or atoms or molecules. Unlike KMT predicted, there are some attraction between atoms and molecules. If there were no attraction between gas particles, they will never condense into a liquid or eventually a solid. They need to, then there are some attractive forces. But under the STP condition, around STP, real gases behave like ideal gases. In reality, no gas is ideal. To describe the behavior of majority of gases near STP, we use ideal gas laws. Ideal gas laws means Charles law, Boyle's law, Charles law, Gay-Lussac's law, Avogadro's law, ideal gas equation. Now you're beginning to understand intermolecular forces play a major role in deciding the state of matter. For example, water is a liquid. Methane is a gas. They have about the same molar mass. Water is 18, methane is 16. Only difference is methane is a non-polar molecule, water is a polar molecule, therefore there could be greater intermolecular force, strong intermolecular force between water molecules. Therefore they condense to liquids at higher temperatures. You can freeze methane also at lower temperature. You can liquefy methane. The strength of attractive forces between molecules determine whether any sample of matter is either gas, liquid, or solid. It all depends on the intermolecular forces. At or near STP, molecules, gases are small, intermolecular forces can be ignored for material that exists as gas. When the temperature decreases, pressure increases. When you cool and you compress, pressure, both. the forces of attraction become important to a point that causes condensation. Condensation is gas becoming a liquid, condense. Ultimately, solidification, liquid to solid, can take place because of the intermolecular forces come into operation as the temperatures decrease. Temperature decrease means molecules of gas, particles slow down. Pressure increase, they are both together, close to each other. Therefore, intermolecular forces can take place. In order to understand properties of liquid and solid, we must look at the nature and the description of intermolecular forces. All right, I'm going to finish after this slide. There are three types of intermolecular forces. Their origins are electrostatic. Now, let me tell you this. Intermolecular forces, we are not talking about ionic compound or covalently bonded molecules. We are only comparing intermolecular forces between the molecules, not within the molecules or within the solid. So there's a chart here. If you look at this, ionic bond is the strongest. Between ions, magnesium and sodium. Sodium chloride has small attraction than magnesium 2+ and magnesium oxide ion, magnesium oxide ion 2-. Their energy is greater than 170 kilocalories. The covalently bonded molecules like methane inside bonds are stronger. They are much higher than 90, at least 90 here. All are larger. But intermolecular forces we are talking about is these three. We already talked about polar molecules. Water is a polar molecule. Water has dipole, oxygen and hydrogen dipole. These dipoles can attract each other, create what we call hydrogen bond right here. That's the intermolecular force. This is lower energy than covalent bonds or ionic bonds. Therefore, these are weaker attractions. But also, dipole, these are OH, NH, FH dipoles are very strong. When you have these three dipoles in a molecule, they are responsible for hydrogen bonding. Therefore, they have very strong attractions. But when you have weak dipoles, like carbon-oxygen has much smaller dipole charge distribution. Therefore, they attract not as strongly as hydrogen bonding. When you have OH dipoles, NH dipoles, fluorine, FH dipoles. So this is, we talked about polar molecules, which are polarities little lower than these three, OH, NH, FH dipoles. So these are collectively, those first three, OH, NH, FH, are called hydrogen bonding. Dipole-dipole interactions are smaller than that. They are present in carbon-oxygen bonds, double bonds, like in this diagram. They are much lower than hydrogen bonding. Even a non-polar molecule like neon is an atom. These two can attract each other because of fluctuation in electrons in the molecule called dispersion, London dispersion. this force is very small. Any covalent molecule, any molecule has this. But when you have one of these, they covers up this. Normally, we don't worry about London dispersion forces in a molecule. If you have one of these, when they don't have hydrogen bonding or dipole-dipole interactions, then London dispersion forces come into operation. Okay, I'm going to start with London dispersion force next week. You guys sign up the chat box.